I have a Feynman theory given by the action. M over 2 dx over dt squared dt. One second. Okay, I'm back. So this is the action. And now we study the following map. S1 that goes to S1. And the length of this S1 is L. And there are two ways to compute raise e to the minus, to raise to the ITH. So that's what we are going to compute. Way 1. Quantum system is given by a vector space V of periodic functions on S1L. With Hamiltonian that equals to h squared minus sign d over dx squared. So function is periodic if psi. So such functions psi are given by sum over k. And here I'll write psi k exponentials 2 pi k x over L. With the I sign, 2 pi I. So h applied to exponential 2 pi I k x over L equals to 2 pi squared L squared k squared and the same exponential. So that's why the race of this object is
what about H bars and M's? Are we keeping track of them?
is the sum of diagonal elements.
I think Timofey means that we must write over 2m.
Now I need to put everything together. IT over H 2 pi square.
Hello, can you hear me?
Yes.
L square. I forgot something. Of course I forgot. H square and 2 here.
And
Times H square over 2m. So this is the sum over k over exponential. 1 second. Okay, do you hear me now?
Yes.
Mhm.
Okay, thank you for letting me know. Yes, I switched my sound off mistakenly. I'm sorry. So you probably asked me something.
Yeah, it was about the factors of m. The h bars you remembered without any prompts, but what about the mass? Are we keeping track of it?
Yes, we are keeping trace of it.
Ah, you wrote it here.
I'm just improving exponent. I have I, and then I have the following thing. Two m 4 pi squared L squared H T K squared.
Wait, what is this? Where's the k squared that is not under the exponent?
Under the exponent.
But where's the k squared as a factor, as the eigen-number, as the eigenvalue?
There is, so eigenvalues are an exponent.
It is
Oh.
eigenvalue of E.
Yeah, sorry. Yeah, everything is correct.
So I can cancel 2 here. And then I'll call this object tau. Including I. So this thing is known in mathematics as theta constant. Okay. Now we will try to reproduce the same thing using functional integral. So how would we do functional integral? It would be called way 2. Functional integral. So here we have this S1, and we go to S1L. Here we say that our trajectories x of t would be decomposed as S classical of t plus psi of t. Now, what can I say about x classical of t? I'd like to say that x classical of t is the classical trajectory. And classical trajectory is trajectory where we move with the constant speed. It's, of course, trajectory of the form x naught plus tv. It's a classical solution. And x classical trajectory has a parameter k. Oh, sorry, I'll call it n. What is the meaning of this n? When t goes from 0 to t, okay, it was t capital. I should put here t capital. X should go from x naught to x naught plus n L. So this is called winding number. The image of this circle wraps n time. So here I have Vn. It's a speed corresponding to this winding. And what I want to ask about psi. Psi should have 0 winding. It means that psi of 0 equals psi of t. We can easily compute Vn. Vn is, of course, what? L divided by t, capital, and here we have n. You see, I'm writing very simple formulas. So when I'm computing something, I'm computing something very simple. Now, so I want to keep this final result on the board. And I'll proceed. S equals S of x classical. And I call it n. Plus psi, and this is S classical n plus S psi. So why I can write it like this? Maxim,
We can just check it.
it's because it's a classical solution. And that's why there is no cross terms in this particular case. Now, integral over trajectories. And here, what is interesting, I have sum over different classes. Topological classes. You see, the space of maps is not connected. It contains of different subspaces that are not connected, different windings. Is sum over n. And here I have exponential s of x classical. N. And it comes as a common factor. And here I have integral over d psi e to the s of psi. Now, what can I say about this object? It is a sum over n, but now I need to compute action on the classical trajectory. Not that hard to do it. M over 2, and here I have T capital, and here I have this constant velocity. So it is a sum of exponentials. Here I have I over h. What do I have here? M over 2 L square over T times N square. And this object, I guess, is not a constant. We need to compute it. By the way, we also have integral over x naught. And this is our famous C of TMH. You see, this thing has nothing to do with the length. It doesn't know anything about the length of the target circle. Okay, here I have this integral, and I assume that this integral is L.
Excuse me, why we multiply this formula on L?
Because we integrate over x naught. Classical trajectories have two parameters, discrete parameter n and continuous parameter x0. We sum over discrete parameter, it is here. But we also need to integrate over x naught. Now we have mystery. No, mystery is written with I. Could it be that these two formulas describe the same thing? They both are sums over integer. However, what is interesting is that expression that you have an exponent is reversed. What you have here is up to factor of 2 pi inverse. We have L square in denominator. We have L square numerator. We have M in denominator. We have M in numerator. The same happens with the Planck constant. So this K are not this N. It's one thing. There is another thing. Here we clearly have no prefactor. And here we do have a prefactor. So what is the prefactor that we have here? I hope you remember this prefactor that we computed last time.
1 over root of t.
Yes, 1 over square root of t. However, as always, t is not coming alone. It goes together with t and that. So there is a summation without prefactor, and there is a summation with prefactor. And if Feynman happened to describe this system correctly, we may predict that these formulas are equal. So actually, this is how mathematical physics is working. Mathematical physics is working in the following way. There are two pictures of two ways to describe the same system. We describe it this way, we describe it that way. And then people have a belief that it is the same system. So formulas should coincide. So in this
But
way,
there's also this factor, the integral over psi.
it is this.
Ah, all right.
So without this integral over psi, we will not be able to get it. And only if we take all factors correctly, we can have this formula. And then we have a prediction. From physics. Saying that theta of tau 0 is theta of 1 over tau 0. And what we have here, what is this factor? It's exactly the square root of things that stands here.
Maybe p square over tau, because there is p square at the right hand side.
Okay, so yes, so it's the question where I put this p square. Okay. So then it's a question how theta function is defined. So if theta function is defined as sum over k, so standard definition of theta function is sum over k exponential of, probably there is p in the definition of the theta function or not. You see, theta k square plus 2 pi I kz.
So p must be at left hand side of equation.
I think that in theta function, I think that in the theta function, people put formula like this.
Could I try
Well-
explain it in Russian? Мне
Well,
кажется, что
Wikipedia puts pi I in front of k squared.
Yes. So pi I tau k squared.
excuse me,
Right.
I could try explaining in Russian. Мне кажется, там p, вне зависимости от того, где его ставить в определении, должно быть либо слева, либо справа в уравнении, что тета от тау 0 равно тета от 1 на тау 0. Ну, там где-то оно должно быть, потому что у нас в одной сумме нету p, а в другой сумме есть p.
Okay, so let me correct myself. You see, so if theta function is defined like this, then how to correct? So it is theta function of so we take pi out of this, out of here. Then this would be tau. Okay.
Okay. So I understand you. Thank you.
So if we come here, we would improve ourselves. Let me take I out of here. Let me put here pi, and let me divide by pi. So altogether, I have 2 pi here. So here I have 2 pi h bar t m l squared. Here I have 2 pi h t m l squared. Very good. So that's why this is tau. 2 pi h t m l squared. So then here we have prediction of something like this. And also then there is a prefactor where we were not quite accurate with pi's. But we hope that with pi's thing would go properly. So here we have something like 1 over square root of tau.
I think it's not tau. Because there is no p under square.
Okay, up to a factor of p.
Well, we lost that factor last time, so it should be there.
Yes, it should
however,
be there.
there's a question of a minus. I'm comparing this with a formula from Wikipedia, and I see that 1 over tau should have a minus. That is perhaps the minus that was lost in front of the action.
In front of the action we had I.
Yeah, but shouldn't it have been minus I? Or maybe in front of the IHT, I don't, hard to say, but
Okay, maybe there is minus in front of IHT. So, okay, we will figure out this minus. Okay. So how we will figure it out? The idea is try to find such a formula. You see, if you go to Wikipedia and if you would like to get a formula, it is instructive, but not that instructive. It's much more instructive to derive it.
of course.
Could
So
you
how
repeat,
to
please? Could you repeat, please, what is this minus? Where it is in our calculation?
So the question is if there is a minus here. We don't see it in our derivation
Okay.
because probably we forgot this minus in our calculations of exponential of Hamiltonian. But
Yes. Okay. Yes.
probably it is like this.
Okay. Yes. Yes.
However, what is much more important is not to know formulas by heart, not to remember formulas by heart. What is much more important is to be able to derive it. So once again, this is a physical prediction coming from physics. And now physicists are coming to mathematicians telling them, look, we predict something very interesting. We predict that this function has relation like this. And then mathematicians say, oh, physicists gave us a formula. Now we may try to prove it. So what is the idea? So now mathematician comes. He knows only this. He knows nothing about physics. How to prove it? How to understand that there could be something like 1 over square root over tau here? Main idea is, when do we have this 1 over square root of tau? We have 1 over square root of tau if we have a Gaussian integral. Do we have here a Gaussian integral? Not really. We have something close to a Gaussian integral. It is a discrete version of Gaussian integral. But we would like to make it a Gaussian integral. So how to do it? We say that it is an integral over dk. Plus condition. And this condition would be that k is integral. Let me even call it p. And here I have a sum over k, and here I have delta function saying that p equals to k. Okay? So now p is real. Here I have this would be Gaussian integral that would reproduce me 1 over square root of tau. But now I would like to understand what this is. How can I get such a delta function? Let me study the following expression. Let me ask, what is this? And I know if p is an integer, this is infinity. However, if p is not an integer, so this is 0. So if p is an integer, it is the sum of ones. If p is not an integer, you may check that you are summing up phases. And this and such a sum goes to 0. And this is called Poisson trick. And Poisson trick says that actually such exponential equals to this sum over k of delta function.
Well, it should be p minus k then in the exponent.
Yes. Sorry, p minus k, I'm not sure. Sorry, no. Just this. Let me try to explain. If p is an integer, then this is an integer.
Oh, right. It's just the 2 pi I k n where integer k is just 1. So it was just yeah.
So we have this great formula. So do you see any physics here? I don't see any physics here. So this is what people call current. I kind of explained why this thing works. Now, what I'm going to do, so let me somehow comment on this. If you have p that is not an integer, you will just you'll just have sum and totally it will give you 0. So how to explain it? In the simplest way. Okay. So here I will refer to mathematics for explanation. So let me see what would happen if I use this Poisson trick. I'm replacing this sum of delta function by such a sum. 2 pi I pn. Sum over n exponential 2 pi I pn. Well, and now I'll take this sum out. And I have integral over dp exponential ip tau p squared plus 2 pi I pn integral over p. But it's a Gaussian integral. And I know how to take it. So I have a square root of 1 over t, probably pi, factor of pi that I don't care. But what will I have? I will have I n squared over tau. And of course, I will get something like pi. So this is a desired formula. So let me try to figure out the sign that I have minus signs. So how do I get it? I'm trying to form the complete square. IP tau p squared plus 2 pi I pn is not a complete square. I need to add another object. That is, of course, n squared over tau. So let me take pi out of it. Okay, I'll rewrite it in the following way. I pi tau p squared plus 2 pn. And it is almost a complete square. To get a complete square, I will add what? N squared over tau. And I will subtract n squared over tau. Okay, so I'm getting it correct. So it is I pi tau p plus n squared minus I p n squared over tau. And then I'm changing variables in the integral, and I actually reproduce this I side. So this is how I'm getting this I side. And there is also something like factor of pi here, and I just don't want to take care about. Okay, so let me tell you what I demonstrated today. in the first half of my talk. I demonstrated the way how mathematical physics could lead to mathematical formulas. We had no idea about Poissonian formula and about modular properties of theta function. We were just studying mathematical physical system from 2 points of view. And surprisingly, we are coming to such formula. And then, in the second half of the 20th century, it happens again and again. And this is how people who are doing mathematical physics create conjectures. In mathematics, like very famous mirror conjecture and many other conjectures. This is a paradigm. Okay, so now we need to make a break. Any questions?
I think
Okay,
that
yes.
there should be a matrix under the S transformation, right? Of the of the theta function.
Matrix.
Yes.
Question. Yes.
I remember the formula is like under the S transformation, there should be a matrix with whose square is 1. So it's not.
So what you remember is the following. This is one-dimensional. Okay. This is one-dimensional formula. Okay, so let me talk to you a bit, okay? Because it is kind of a question. Of course, this could be modified if you have a matrix T A B. That is sum over K exponential I pi. And here we would have the following thing. Tau K K. Okay? Plus 2 pi I K Z. That is the vector. And now you may do the same mathematical trick. Okay? You may have mathematical proof. In a very similar way, you replace this together with the sum by the integral over dp exponential I pi p tau p plus 2 pi I. Okay, I don't even want to consider this term. Mathematical proof for d equals 0. And then we put in p times n times 2 pi I exponential and sum over n. And then do exactly the same thing. And tau would be inverted as a matrix. So this is a mathematical proof. And then let me ask you, Could you imagine the proof of this coming from physics?
No, I don't.
Should it live on a torus then? With different winding numbers?
So it is a question. I'm not
Maybe it's a
saying
map from a torus to the same torus.
so.
From physics.
So from physics, you may say, so it is a homework. What would happen if we map from S1 to the torus?
Oh, right, from S1, not from a torus to a torus, but from S1.
In what follows in my course, you would see that this formula is important even if we are mapping from the torus to a torus. It will be a very important formula later on. But I do not want to load your mind. I'm trying to give you information piece by piece, okay? So you may think about it. So here is the mathematical proof. Here is the equation, how S1 is mapped to a torus. Okay? Now we will have a break. Okay? Let me continue. So, what I will do now, I will try to modify my problem. And now I'll tell you how physics, mathematical physics, and mathematics are coming together. So up to now, it was only mathematical physics and mathematics. Now let me put in some physics. In real physics, there was a dispute. If vector potential has a physical meaning. So there was a magnetic field. And magnetic field is known to be the rotor of curl of the thing called vector potential. And in most experiments, we observe only beta, only B. In most experiments, only B was observed. And therefore, that's why people were thinking that this A is something auxiliary, not a physical quantity. Conjecture was that A is just a mathematical object.
Excuse me, camera lost focus and they're very blurring.
Okay, I am sorry. Thank you very much. I'll try to improve it.
now it's find focus and it is able to see all.
Okay, so this is just a mathematical object. But there were people called and Bohm who said, no, we may be able to observe A. So how did they did it? So suppose you have a solenoid. So we have current here. So it means that we have magnetic field B inside. No B outside. So the question was, is it possible to detect the current in the solenoid if you do physical experiments outside the solenoid? So experiment was like this. They took electrons and they went this way and that way around the solenoid. So A was not zero outside. And they measured the interference. So it was not zero. So electron traveling around the solenoid was coupled to A itself. So it is a physics. It's a piece of physics. Now, how do we see this physics in mathematical physics? We studied it last semester. The Lagrangian, okay, the action of the non-relativistic electron plus the coupling to electromagnetic field, and here I'm writing this vector potential. And we already have seen that this leads to a Lorentz force. However, Lorentz force, it depends only on B. However, when we are writing quantum mechanics, in the form of, I'm sorry, I need to change the pen, of integrals over trajectories, we will study this. And this S depends on X and parametrically on A. And since this A comes to the action, we may assume that we will see the effect. So here we are moving to mathematical physics. And now let us consider the simplest model. So space dimension is 1. And of course plus time. So when space dimension is 1, there is no B. It means that B is identically 0. Because it's a two form, you cannot have a two form in dimension 1. However, we may see Aharonov Bond effect, Aharonov. Bomb effect in symmetrical physics. So what we will do? We would study the same quantum mechanical system with non-trivial vector potential for periodic or for compact for S1L being the space. So we will write S that we study plus A small X dot. That's it. And we will study integral over dx that depends on X and parametrically depends on A. So this is conjecturally exponent of IT over H, IT capital over H. And here we will see Hamiltonian depending on A. So the game that we are going to play right now would be, we will compute this, and then we will guess this. And after we will do it, we will look on this mark. What would be the quantum system here? What would be the value or behavior of the functional integral on the left? Why they are equal to each other? So computation from functional integral that we called way 2 is easily modified. So equations of motion are, of course, m x2 dot equals to 0. Look, this thing is almost a total derivative. It is not a total derivative since x is periodic. So would the target space be a line, we could just ignore this term. However, we cannot ignore this term completely. Now, once again, we write x classical as x naught plus n l plus, and here I have t, and here I have a velocity. And in the velocity, I have, of course, k times l. So when over t. Or probably I call it n. Now I'm plugging this x classical here. So x naught decoupled. What is left is s classical now, depending on a, is okay, let me write it again. M L square n square. Here I have t without square. But now look, this term, Aharonov-Bohm term, would appear. And I will get what? I will get here I take a derivative, I have a times L over t, integrate by t, I get plus AL. Of course, times L. So what is the result of it? The result is that theta function would be modified to, theta constant would be modified to theta function. With z equals to AL. Great. You know that I like this function. So theta function is not theta constant. So we see that A field could be seen in the way too. So functional integral predicts some modification. Now, what does it mean in the way one? So there's the question. How to modify the pair vector space and Hamiltonian, including A? So before we will do it, let me make the following observation. Theta function of tau z equals theta function of tau z plus 1. So there should be some modification of what? We may think that we are modifying V or we are modifying H. And it is not easy to understand what to do. However, we may go to Poisson formula. To get understanding. So what would Poisson formula tell us? So now I already write it like this. It's an integral over dp. Okay, I'll be not very accurate with pi's and other stuff. Plus, now I have 2 pi I times p. And now I have here a sum over k. And what do I have here? I have exponential 2 pi I p k. It is integral over 2p. I forgot something. and also tau. Exponential of IP p squared tau plus, okay, sorry, no, not A, but Z. So Z is AL. Plus 2 pi I pk. Okay, so what has changed? Instead of one term, I have two terms. So I am not afraid. I am not afraid. I will just group it and say that it is 1 over square root of tau. And here I'll have exponential of what? Previously I had exponential of k square over tau. Now I'll have an exponential of k plus z. Ah. Here I am. This is the formula that I want. Not as a mathematical formula, but a hint. Remember that this tau was actually t. So 1 over tau here was t times something. So this is 1 over. So when I'm doing this formula, I have the following thing. I know that this square root, 1 over square root of t tau would be cancelled out. But what I see from this is that I will get something like exponential of minus IP k plus z square t times something else. So now the question is, how to interpret it? So Maxim, do you know how to interpret it? That I have a shift of k by z.
Maybe how null of energy.
Have what?
Um,
So energy k square is shifted to k plus z square.
yes. Yes.
So what are the, so how it could happen? You see, I'm asking you to see if it's a trivial for you. So we go from mathematics back to physics. Sorry, from mathematics back to mathematical physics. What this could be? So the question was, what is a new Hamiltonian and what is a new vector space. Tim, do you have an idea?
Well, I guess the Hamiltonian is p shifted squared, so it's like p plus z squared, and the new vector space is not periodic functions, but quasi-periodic, periodic with some phase.
So surely you are joking, Tim. If you do both, you will get the same result.
Oh, yeah, I guess then we just need one of this.
Yes, so Bitcoiner has a good idea. Okay, Bitcoiner was faster.
Sorry, Professor, can you shift or move the camera to the right? Okay, thank you.
So, interestingly enough, Bitcoiner was faster. He said, look, let Hamiltonian be the same. However, functions would be quasi-periodic. So what does it mean? Hamiltonian is still IH d over dx squared with a minus. However, psi of x plus L would now be quasi-periodic. Let me try to write it like this. So what would it mean? In this case, it would mean that psi of x is I to the I k plus z. Sorry. I k plus z. Okay. 2 pi. X over L. So for such psi case, Hamiltonian, so let us check that psi kz of x plus L is e to the, okay, 2 pi I z. Psi kz of x. Quasi-periodic. And Hamiltonian would give exactly this result. Or another option. Functions are the same, but Hamiltonian is EH d over dx plus a squared. And this is another alternative. Anyway, answers are different. Now, there is a good exercise that nobody would do. But it is very useful to make this exercise. I'm sorry. Hello? Okay. So there are cheaters. I'm sorry. So this is another point of view. Now, exercise that you will not do. However, it's very important exercise. Compute k of x in x0 xt in a system on S1L in the, let me call it Aronov bomb. Aronov bomb. Potential A. Get answer in terms of theta functions. Hint. So this is S1L. You have X naught. You have XT. So you study trajectories like this, but also trajectories like this. Sum over all trajectories. Get nice formulas. Check factoriality. Okay. So today I'm in a good mood. Today I want to say only good things about functional integral. My time is out. So let me tell you what you would probably have tomorrow. Tomorrow, Maxim Leenzon is starting his course that is parallel to my course. And we will join when we will discuss two-dimensional theories. So he would speak about complex structures on algebraic manifolds. Okay? Because in the main definition, where we have function from geometrically enriched covariance. Geometrically enriched would mean complex structure. In real dimension so that's why you need to know something about it. And he would explain. So, okay, I have something in the chat. So come to his course. And to his, not to his course, to his part of the course. And you will hear about pre-sheaves, sheaves, rings, a bit about spectra, topology, and Zariski topology, complex structures and their deformation and all that. Okay? So while I'll do some mathematical physics, he would do mathematics, and then we will join. Our lines together. Okay? Any questions?
Yes, Professor.
Sure.
It's my first time to see what you mentioned, the Poisson trick, and
Yeah.
I think it is a divergence in the means of mathematics of analysis, and another similar problem is in the complex function Gaussian function integral during your calculation, I think the function the integral also divergent. So how,
It's convergent because it is highly oscillating integral.
pardon, what integral?
Integral dx
Yeah.
e to the I t x squared
Yeah.
is convergent. It's conventionally convergent. So this integral is convergent.
Oh, it's convergent.
Yes.
I can see it because this one is in the unit circle, is on the unit circle. You
It's
integral
not
over.
on the unit circle. Okay. The integral dx e minus t x squared is absolutely convergent. This integral is conventionally convergent. What does it mean? It means that if you take limits from minus L1 to L2, and if you take L1 to infinity and L2 to infinity, such a limit exists.
It's independent L1 and L2.
It
Go to
doesn't matter.
infinity.
It doesn't matter. It exists in both ways.
Oh, okay.
Because it's called highly oscillating integral.
Highly isolating.
So how do I know that it is convergent? Because I may evaluate from L2 to L2 prime e to the dx e to the it x. X squared. So you may do it yourself by evaluating this object. This exponential is oscillating like this. And you may compute it in the following way. You see, it's because it's oscillating. And if you take L2 square equal n and L2 prime okay, so
I'm sorry for interrupting. Isn't the simplest way to see it is to change variables to something like y equals x squared? And then we have an oscillating function divided by the square root, and that's like first year analysis.
Okay, so maybe we can try to evaluate it this way. Thank you, Tim. So let us take y equals x squared. Then dy is dx times x with a factor of 2 standing here. So let us change variables. We will get here y. So dx is dy divided by x. That is the square root of y. So we have a product of the oscillating function times this. You may say that dy over square root of y is not falling fast enough, but there is a theorem in mathematics that the product that Tim mentioned, that the product of oscillating integral times the decaying function is convergent. Tim, do you mean that?
Yes, exactly that. And also there's no problem at 0 because it's a square root and it converges.
Yes, but we are evaluating it away.
Yeah, but I mean this way you can just straight just calculated from minus infinity to infinity without.
Okay. So this is okay. This is our reply to the question that this thing is not convergent. It is perfectly well convergent.
Yes, I see it. Okay, and my first question is, I don't know the details why Poisson trick hold, because I see it the sigma the sum is not convergent, e to the 2 pi I pn.
Okay. So now let us try to talk more about Poissonian trick. Okay. What does this mean? What is this? So idea is that this is not a function. It is a distribution or current. In different literature, it's called differently. Actually, we would like to say that this is sum over n delta function of p minus n. So delta function is not a function, right? It's a distribution. So let us try to make mathematical statement out of it. So to make mathematical statement out of it, we need to show the following. That suppose that since it's a distribution, we need to show the following. Suppose we have function phi of p, and here we have an integral, and this should be equal to sum over n. That we want to show. Oh no, it's definition of delta function. Phi of n if such a sum exists. So it's enough to consider function phi finally supported, finitely supported. Okay? So it means that we need to show that okay? So this is the mathematical meaning of Poisson formula. Sorry, and here I need to put integral over dp. Now let us try to see how we can prove it. So first of all, it is enough. So we have this line 0, 1, 2, etc. It is enough to prove it for the functions phi of n, for the functions phi of x that are finitely supported. So now let us try to do something about it. You know, I have the following proposal. We may take as phi of x the following functions. So sometimes there are also called theta functions, but other theta functions, like step functions. So what is a step function? Consider phi of x that equals 1 for x between minus 1/2 and 1/2. Okay, maybe it's better to call it a and b. A is bigger than minus. So here I have 0. I want to put it here. A is bigger than minus 1. And here I have b, and here I have 1. Okay? Let me consider such function. Phi ab that equals to 1 for x between a and b, and phi ib equals 0 elsewhere.
I'm sorry, Professor. We're really pushing the 2-hour mark, and as Bitcoiner points out, there's a good introduction to all of this on Wikipedia, and this is like more or less basic material, not something special. So perhaps it could be left as a
Okay.
kind of, I'm not. I don't have anything against that question, but looks like there are quite a lot of sources and resources where you can find explanations of these formulas with any degree of formality.
Okay.
Yes,
It's
okay.
just
I can
it's,
check this integral. I see it. We can check by the step function, and I know what this
Yes.
this summation mean. Okay.
You can put here step function, you will get something like finite sum, and you can check.
Yeah. I see.
You see, Tim, I'm sorry, but my habit is to answer all questions.
yeah, I understand it. Yeah.
But for the case of theta function, the proof is kind of conceptual. Okay?
Okay, thank you.